Hello, everybody. Welcome back. In this video, we're going to talk about an absorbing state for a Markov chain. Now, an absorbing state is a state that once you hit it, you can never leave. And I mean ever. Okay, so the first thing we're going to do is look at what an absorbing state looks like from the point of view of a transition matrix. I have a discrete time Markov chain on the discrete state space 1, 2, 3, and 4. And you'll notice in the 2 row, I can only go to state 2 with probability 1. So if I start at 2, I'm stuck at 2. If I start at 1, I may move to 2, and then I'm stuck at 2. If I start anywhere, I may move to 2, and I'm stuck at 2. Although it doesn't actually matter that I can get to 2. So an absorbing state is if you're there, you're stuck. So even if there is like state 2 doesn't communicate with the other states, it's still an absorbing state. If you're at state 2, you're stuck there forever. Now, a classical example of an absorbing state is the gambler's ruin problem. So suppose you are playing a game that has trials, maybe you're approaching a craps table and you've got, each time the dice are rolled and you come up with a certain amount of money and you have a betting strategy. And it may or may not be Markovian. Maybe, how you bet depends on what happened in several past bets, but it might be Markov. The point is, it doesn't matter. It's a stochastic process, and I'm going to let xn be the total amount of your money at time or trial n, and it goes up and it goes down. But if it hits 0, you're stuck there forever, or at least you should be. So that's an obvious example of an absorbing state. There are many more that occur in nature, or at least in our models of nature. But sometimes you want to bring an absorbing state into a problem where it's not there, it's not supposed to be there, but it makes some calculations easier for you. So I have a ridiculously oversimplified model of the weather. From day to day, the weather is either sunny, cloudy, or rainy. I'm going to denote that with an S, C, and R. And of course, that's problematic because it could be sunny in the morning and rainy in the afternoon. But suppose this is well defined for us, and suppose that we assume that the weather transitions from day to day follow a Markov chain, which is also not a reasonable assumption. A storm comes in and maybe brings a weather front with it, and some weather hangs around, but it's an oversimplified model. So weather, sunny, cloudy, or rainy, the assumption is the weather from day to day is a Markov chain. So the weather today is only dependent on the weather yesterday, or maybe not, but it's not dependent on anything further back. And I'm going to suppose that we know a probability transition matrix, which is given right here. So for example, if it's sunny today, it will be cloudy tomorrow with probability 0.2. So I have a question for you. Given that it was sunny on Monday of this past week and not cloudy on Tuesday or Wednesday, what is the probability that it will rain on Thursday? So our sort of starting time point here is Monday. And in the language of Markov chains, I'm going to call that time 0. So here are some slots or positions representing time 0, 1, 2, and 3, or equivalently day Monday, Tuesday, Wednesday, and Thursday. And I do know that it was sunny on Monday. And I don't exactly know what it was on Tuesday or Wednesday. I just know that it was not cloudy. And I want the probability that it's rainy on Thursday. So in Markov chain notation, we would write this like this. I want to know the probability that x3 is R for rainy, given that x2 and x1 are not cloudy, and also given that x0, the weather on day 0 or Monday, was sunny. So before we solve our problem, I do want to talk about a few common pitfalls that people stumble into with a problem like this. One thing you might think is that by the Markov property, this probability is equal to this probability. But that's not true. The Markov property says that where we go depends on where we are, or at least where we knew we were last. We talked about how you can skip time steps. But just because I know it is not cloudy on day 2 doesn't tell me what it is on day 2. So you actually can't get this from the Markov property. Now, another common mistake would be to say that this probability is equal to the probability that it's rainy on day 3, given the last actual piece of information that is solid. We know that it was sunny on day 0. This is also not true by the Markov property, because even though we're not given what happened on day 1 and day 2, we do have some information there that we can't ignore. So we're going to figure out how to do this probability. But before that, I want to give you just one more pitfall. So the probability, for example, that x3 is not rainy given x2 is cloudy, this is the complement of the event that x3 is rainy, and we're in the universe where x2 is cloudy. So you can write this as 1 minus the probability that x3 is rainy given x2 is cloudy. But the probability that x3 is rainy given x2 is not cloudy. This is not 1 minus the probability that x3 is rainy given x2 is cloudy. And conditional probability just doesn't work like that. If you were to write this probability out, you would have something in the denominator, and I would encourage you to do that. Write this out as it's, by definition of conditional probability, as the probability of an intersection over the probability that x2 is not cloudy. You can change that denominator to 1 minus the probability that x2 is cloudy, but no matter what you do, you can't get to this right-hand side. So complements don't really work that way when the thing is after the conditional line. But back to the problem. How are we going to solve this? So the first thing I'm going to do is rewrite this big conditional probability by definition. I'm going to write it as the intersection of all of the events, that probability, and I'm going to divide by the probability of all of the events after the conditional line. Now, it's a Markov chain, and I don't know where we started, but I do know about transitions. So I'm going to rewrite this big fat joint probability as the probability of this stuff given where we are at time 0 times the probability of where we are at time 0. And I'm going to do the same thing in the denominator. I don't know the probability distribution, the initial distribution at time 0, but it's okay because they're going to cancel, leaving us with this. Now, I still have the same problem I had before. I want to know what's going on at time 3, and I've got what happens at time 2, but not really. I only have what doesn't happen at time 2. So here's where the absorbing state comes in. So how can we compute this probability? We have several options, and the first, we're going to do it by brute force. So I want to know, I'm given that we're starting sunny on day 0, and I want to know now the probability that we're not cloudy, then rainy. So I can write a little table like this. We're always starting sunny, and then we could go sunny, sunny, rainy, 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 sunny, rainy, or rainy, rainy, sunny, as long as we leave off, there's no traveling through cloudy. The probability that this first row occurs, that we go from sunny to sunny, and then sunny to sunny, and then sunny to rainy, I'm going to use the Markov property. The sunny to sunny probability is 0.7. The sunny to sunny again probability is 0.7, and the sunny to rainy probability is 0.1. I'm going to do the same thing and compute the probabilities for all of these rows. Now, these are disjoint events that are possible outcomes for the event we actually care about. So I get to add the probabilities, and we get 0.128. That wasn't that bad, but you can imagine if there's more states and longer time, and maybe more states we want to avoid, this can get pretty bad pretty fast. So that was the numerator. Let's look at the denominator of the original conditional probability that we want to find. So the probability that it's not cloudy on day 2 and it's not cloudy on day 1, given that it was sunny on day 0. Again, I'm going to kind of draw or write out or list out all the possibilities here. So we're always starting sunny, and then I want to be not cloudy and not cloudy. So sunny, 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 rainy, rainy, sunny, or rainy, rainy. And we have the probability of transitioning from sunny to sunny is 0.7, from sunny to sunny again is 0.7. And if you do that for each row, you get a bunch of probabilities, and you can add them up because these are disjoint events, and all of them contribute to it not being cloudy on day 2 and day 1, given it was sunny on day 0. So when you multiply these and add them up, you get 0.63. And going back to our original problem, what is the probability it is rainy on Thursday, given that it was sunny on Monday, and also given that it was not cloudy on Tuesday or Wednesday? We rewrote that. We took some time to rewrite that. We had a numerator and a denominator, and our numerator probability was 0.128. Our denominator probability was 0.63. And so when we divide, we get the answer to our original question. We get 0.2032. This was our brute force method, and you can imagine that it's going to get kind of bad kind of quickly. And this is where absorbing states come in. Here's the probability we want to find. And we have a Markov chain Xn, and it runs according to a given probability transition matrix. And I'd like us to take that and create a new Markov chain. I'm going to call it Yn. It's going to move through the states sunny, cloudy, and rainy. And it's going to have a transition matrix that looks like that of the X chain, except the cloudy state is going to be absorbing. So the state that had the not equals in the probability we care about is going to be made to be an absorbing state. Now imagine running the X chain and the Y chain in tandem. In tandem, I mean using the same sort of random input. You know, if you were trying to decide whether it was sunny or cloudy or rainy, you might have a random number generator, and you could compare those random numbers that it generates to values in the matrices, but using the same random number for both the X chain and the Y chain. And so if the X chain is rainy, then sunny, then rainy, then rainy, then cloudy, then sunny, then rainy, the Y chain is going to go along as the X chain, rainy, sunny, rainy, rainy, cloudy, but then it's going to be stuck at cloudy and finish off with cloudy, cloudy, cloudy. Again, when the X chain hits cloudy, the Y chain hits cloudy, and therefore the Y chain ends in cloudy. And if the Y chain ends in cloudy, that means it hit cloudy at some point, and that's equivalent to the X chain hitting cloudy at some point. So we have some equivalent events. The probability that it is rainy on day 3 and not cloudy on days 2 and 1, given that it was sunny on day 0 for the X chain, is the same as the probability that it's rainy on day 3 for the Y chain, given the Y chain started in the sunny state on day 0. Again, if the Y chain ever hit cloudy, there's no way it's going to end in rainy. And if the Y chain ends in rainy, there's no way it had ever hit cloudy. So these two events in these probabilities are equivalent. Now this is just a 3-step transition probability for the Y chain. And we know we can compute 3-step transition probabilities by taking the transition probability matrix, in this case Q, cubing it, and grabbing the sunny to rainy entry. So this is going to take care of the numerator for our original conditional probability. We rewrote it as a probability over a probability, and this one was in the numerator, and this one was in the denominator. Okay, so for the denominator, I want the probability that x2 is not cloudy and x1 is not cloudy, given that x0 is sunny. And in the Y chain, that's equivalent to the event that y2 is not cloudy, given that y0 is sunny. How can I get this probability? I can either look at, I will look at the square of the Q matrix, the probability transition matrix for the Y chain. And in that square matrix, I can either pull out the sunny to sunny and sunny to rainy entries and add them, because those are the two ways to not be cloudy. Or I can take 1 minus the sunny to cloudy entry of the Q matrix squared. Okay, so let's pull all the pieces back again. This was the original problem. We spent some time to rewrite it like this. We discussed this new Y chain where we can rewrite these X chain probabilities in terms of Y chain probabilities. And I'm going to go with the complement event for the denominator. So I'm going to rewrite the probability that y2 is not cloudy given y0 is sunny as 1 minus probability that y2 is cloudy given that y0 is sunny. The numbers we get here, if you take that Q matrix and cube it and take the S to R entry, that's 0.128. If you take the Q matrix and square it and take the S to C entry, that entry is 0.37. And when you put it all together, you end up with an expression that looks like this in general, and the numerical answer of 0.2032. Okay, so since we have this Markov chain and transition probability matrix all set up and ready to go, let's ask and answer a few more questions for this example. So we asked the probability that it was rainy on Wednesday, given it was not cloudy on Wednesday and Tuesday, and it was sunny on Monday. That was the old question, but now I want to add to it that we know it is not cloudy on Thursday. So before, I didn't have any information about Thursday. So I still want ultimately the probability that it rains on Thursday, but we've already ruled out cloudiness. So before I had this probability and we computed that to be 0.2032, and now we're going for this probability. So note the inclusion of the fact that on day 3, it is not cloudy. So before doing this, which one of these probabilities would you expect to be smaller and which one would you expect to be larger? So both of them are computing the probability that it's raining on Thursday. And with one exception, we have all of the past information the same. But for the second event, the probability in the second event, we have already ruled out cloudiness for Thursday, making rainy and sunny more likely than they were before. So I definitely expect this second probability here to be larger than the first probability. And that first probability was 0.2032. So keep that in mind for the comparison. So here's the new thing we want to find. And I'm going to start running this out the long way. But once you're comfortable with this, you may want to skip a few steps because you'll know where this is going sort of every time. So by definition of this conditional probability, I'm going to write it as a probability of everything intersected over the probability of everything after the conditional line. And to get back into that conditional land where the transition probability matrix can tell us things, I'm going to take a moment to rewrite these as the conditional probability of all of this stuff given x0 equals sunny times the probability that x0 equals sunny, and all of this stuff given that x0 equals sunny times the probability that x0 equals sunny. So again, these probabilities cancel, which is a good thing because we don't know what they are. So I'm left with a numerator and a denominator. And so for the first one, probability that x3 is rainy and x2 is not cloudy and x1 is not cloudy and x0 is sunny, I'm going to use my y chain defined just as it was before, where cloudy is an absorbing state. If I start sunny on day 0 for the x chain and I'm rainy on day 3, I may have been sunny, rainy, or cloudy in the meantime. But if I'm looking at the y chain, which is kind of running in tandem with the same random input, if I start sunny on day 0 for the y chain and I find myself rainy on day 3 for the y chain, I know for a fact that the x chain was never cloudy in between. So in other words, this event is equivalent to this event. For the denominator, the probability that x3 and x2 and x1 are all not cloudy given x0 is sunny, the only way this can happen, or sort of I should say if and only if, the y chain at time 3 is not cloudy given the y chain at 0 is sunny. So I can get this probability as 1 minus the probability that the y chain at time 3 is cloudy given that the y chain at time 0 is sunny. And remember, this is not the only way you can do it. So if we're not cloudy, we're either sunny or rainy. So I can write that denominator instead as the probability of going from sunny to sunny in 3 time steps for the y chain, plus the probability I go from sunny to rainy in 3 time steps. But I'm going to use the complement here. And I've got my Q matrix, so I cubed it in both cases. For the numerator and denominator, in the previous example, we cubed it and we squared it, depending on where we were. And we get 0.2607, which is in fact larger than the number we had before, 0.20, I already forgot, but it's definitely larger. Okay, so in this video, we talked about absorbing states. We defined what an absorbing state was, kind of informally. And we talked about absorbing states occurring in some problems and models out there in the world, like the gambler's ruin problem. You run out of money and you're stuck there, hopefully. And then we talked about bringing an absorbing state into a problem for a Markov chain to help us find some probabilities where we're not exactly given the past history of the chain, we're given where we kind of weren't. And that was a lot of fun and certainly easier than the brute force method for more realistic problems. In the next video, we are going to put the Markov property, we're going to put a longer history into a Markov framework. So where we go might not just depend on where we are, but where we were the day before. Now that alone is not Markov, but it is if you rewrite it in the right way. So hopefully I will see you in the next one.